Okay, what is a graphical graduation? Graphical graduation is a method where we manually draw a smooth curve through crude mortality data. It's typically used when we have a small data set because more advanced methods may not perform well. The main goal is to balance smoothness with adherence to the actual data. However, since the curve is drawn by hand, the process is subjective and depends heavily on the analysis judgment. And before drawing the curve, we prepare the data. If the age range is wide, we split it into groups, like below 60 and above 60, because mortality scale differ. We often transform the rate using log or logic to stabilize the scale. When data are sparse, we combine ages until at least 5 them appear in each group. Then we plot the group mortality rates at either the midpoint age or the weighted average age. Okay, next, after plotting, we add a 95% confidence interval around each rate. This helps us understand the uncertainty in the estimate. Then we draw a smooth curve that passes through roughly 95% of these intervals. The key challenge is achieving a good balance. The curve must be smooth but still close enough to reflect the true pattern of the data. Too close mean too jagged, too smooth mean ignoring important trend. Okay, once the curve is drawn, we check its smoothness using first, second, and third difference. These help detect irregularities in slope and curvature. If needed, we adjust the curve manually, a process called hand polishing. Finally, we test the curve adequacy using statistical tests like chi-square. Graphical graduation is useful with small dataset and a low expert judgment, but it is subjective and cannot give high
When you don't have
precision.
enough debt data for your group, you can still estimate their death rate by using standard table as a guide. Standard table impose a basic structure on our new graduation. However, the level of mortality rate might be different, but the progression of rate should be fairly similar. The crude rate of Q estimate are graduated by attempting to find a simple formula relating our new data to the standard table mortality rate, denoted by Q as X and mu as X. These are the possible functions that can be How to choose an appropriate standard table. This is guided by the type of life under consideration. Firstly, for assured life, we can refer to table A6770. Next, for annuitants who sign an annuity contract, can refer to table A90. For pensioners, table PA90 can be referred to. And lastly, for population-based study, ELT15 table can be In summary, we must consider the class of lives being graduated such as assurance, genders, and geography. Secondly, the period of time underlying the standard table. Next, the range of age being covered, unusual features of the standard table, and lastly, the method used to graduate the standard table. And lastly, the selection characteristic of the standard table.
Now we need to know the relationship of the data calculated. Firstly, plot the data of crude rates and standard table rates to find is it in a linear line graph. Now we need to know the relationship of the data calculated. Firstly, plot the data of crude rates and standard table rates to find is it in a linear. Second, plot crude rates over standard table rates for y and h for x. Now look and determine will it get into the ratio plots? Second, plot crude rates over standard table rates for y and h for x. Now look and determine will it get into the ratio plots? Second, plot crude rates over standard table. Lastly, transform to log and plot against h also. Then determine will it also get into the logarithm graph? Lastly, transform to log and plot against h also. Then determine will it also get into the logarithm graph? Lastly, transform to log and plot. After doing all that, now we will determine the parameter of theta by using WLS, which is width least square, where it will minimize the sum of square of deviations. After doing all that, now we will determine the parameter of theta by using WLS, which is width least square, where it will minimize the. By using this formula of Qx to calculate WLS, where Wx is our weight of each x. By using this formula of Qx to calculate WLS, where Wx is our weight of each x. By using this formula of Qx to calculate WLS, where Wx is our. There are some advantages of using standard table graduation in this formula, which is the first one is use strong peripheral information. Second, works with sparse data, which is large data, and produce smooth rates and stabilize our extreme edges, which is x, and easy to implement for the data. There are some advantages of using. However, there are also some disadvantages of using standard table graduation. Firstly, selection of table can sometimes be hard to interpret and understand. Second, there will also be adherence where data errors and have biases. Data is limits flexibility and coordinates for us, and lastly, it is not suited for the big data.
Now, I'll be covering the graduation by mathematical formulas. This is the preferred method when we are dealing with the large data sets, like the standard life table. Unlike the graphical methods where we drew the curves by hands, here we use the parametric equations. This guarantees that the curves is smooth, so our main challenge is just to find the right formula that adheres closely to the data set. Our mathematical approach starts with the classic mortality law. First, Gompertz in 1825 modeled a mortality as a simple exponential curve. Then, Macquerham added a constant A to account for non-age-related deaths like accidents. Finally, as the data improved, Perks introduced the fractional formula in 1932 to better capture the shape of the all mortality across all ages. Modern actuaries often use the logic transformations. It stretches the probability scale from 0 to 1 out to infinity, which makes it easier to model using the polynomials. The hard part is finding one formula for the whole life. We have a high infant mortality, a teenage accident harm, and then a normal aging. To solve this, tables like the Australian National 1960 over 62 actually combine three functions into one complex equation to capture every single phase accurately. To organize this, we classify models into the Gompertz-Macquerham family based on how many polynomial or exponential terms they use. We then use computers to calculate the best fitting parameters using statistical methods like the maximum likelihood or weighted least square to minimize the error between our formula and the real data. The biggest advantage here is objectively, there is no human bias. We can statistically test how good the fit is. However, this method is very difficult to use on the small data set. It can be risky if we try to predict the mortality rates outside the age range of our dataset.